Good morning students, my name is Prasant. I have been working as a physics faculty in Tungal College. Today we are going to discuss second PU 5th lesson, magnetism and matter. The lesson name is magnetism and matter. Magnetism and matter. I want to explain the introduction. Introduction. A kind of iron ore has a tendency. A kind of iron ore has a tendency to attract. Attract pieces of iron and other materials like nickel, cobalt, is found in a place called Magnetism in Greece. This is the first basis of finding magnetic materials. This magnetism place, based on this magnetism place, they gave the name. In Greece, the ore of iron is called magnetite, and the iron from magnet is called magnet. Here, the kind of iron ore has a tendency to attract the piece of iron and materials nickel, cobalt is called. This total phenomena, attracting phenomena, is called magnetism. The attracting phenomenon exhibited by magnet is called magnetism. This is about introduction of magnetism. I am going to repeat one more time. A place called Magnesia in Greece, they find that a ore of iron has a tendency to attract pieces of magnetic material such as iron, cobalt, nickel. This ore has a tendency to attract. Such a ores are known as magnets, and apart from attracting property, it also shows directional property. What is meant by directional property? We are going to discuss now. Here, next point, a freely suspended piece of magnetite comes to rest in north south direction of earth. North and south direction of earth. See, assume this is a free surface. From this I am suspending a magnet needle. After some time, the magnet needle comes to rest in geometric north and south direction. This is geometric north. This is geometric south. geometric south. The end which points towards the geometric north is called, see this is the end pointing toward the north, so this is known as north pole. North pole. The end which points toward the south is known as south pole. So from this experiment, I can say, from these two things we can say the magnet has a tendency to attract other materials. This is known as attractive property. A freely suspended bar magnet come to rest in the north and south direction of earth. So this is known as directional property. By using this directional property, the sailors are used as a magnetic compass. By using this magnetic compass, they travel from the unknown places. They travel to the unknown places, and this directional property used to explore them in different places. Next, now I am going to explain the some other properties. Here, what we are going to say, naturally occurring magnets are irregular in shape, and having less strength. This is about natural occurring magnets have the irregular shape and less strength, so they won't use. Now artificially prepared magnets have regular shape, Example, bar magnet, ring magnet, horseshoe magnet, magnets. Example, sir, where they can use? Best uses. Magnets are used in speakers, ATMs, and security system. This is about applications and introduction. Now we are going to discuss bar magnet. From the number of experiments, they concluded that magnet has two poles. Now we are going to discuss about bar magnet and properties of the bar magnet. Bar magnet. Sir, it is in rectangular shape or cylindrical shape. So from the experiments, they concluded that magnet has two poles, namely north pole and south pole. If you bring another magnet nearer to the this magnet, like poles repel each other, so they show repulsive force. If you bring the like poles together, there is a repulsive force. Here repulsion occurs. Here, if you bring unlike poles together, attraction occurs. Trying to move in this direction. Attractive force. So from this we can say magnet has two poles. They are north pole and south pole, and like poles repel each other and unlike poles attract each other. Now we are going to discuss the properties of the some other properties of the bar magnet. In this bar magnet, what are the things we are going to discuss? This bar magnet, I want to explain the pole. First, what is meant by pole? Say I already mentioned to you, bar magnet has two poles, north pole, south pole. Sir, if you see the distance, these are the known as, I will mention A, B. These are known as extreme ends. A and B are extreme ends. Extreme ends. Now I want to mention what is meant by pole. The point, the definition of pole, the point where the magnetism is concentrated is called magnet, is called pole, sorry. The point where the magnetism is concentrated, pole. What is meant by magnetism? The property of attracting other species or repulsing other species is known as magnetism. So if you, is called pole. The property of attracting other species is known as magnetism. The point where the magnetism is more, that is known as pole. Here the poles are concentrated somewhat nearer to the somewhat into the magnet, into the bar magnet. If you consider here, all the distance are measured from the center. So center I am giving O. One end is at a distance of L, other end is at a distance of L. This 2L is known as magnetic length. 2L is known as this 2L is known as geometric length. L is known as geometric length. The distance between north pole and south pole is known as, I will write the distance between north pole, north and south pole. The distance between north and south pole is called magnetic length. Magnetic length. The magnitude of magnetic length, I am going to write this. I am going to write ML. Geometric length I am going to represent as GL for convention. So I can write magnetic length ML equal to 5/6 of GL. So magnetic length always less than the geometric length. So poles are not concentrated extreme end, they concentrated somewhat inside the ends. This is about bar magnet. Now we are going to consider this bar magnet as a magnetic dipole. The strength of, what is meant by strength? The repulsive capacity or attractive capacity of a magnet is expressed in terms of pole strength. The ability of repulsion or expression, one minute I will write, pole strength. The pole strength. Pole strength, it represents the ability of attraction or repulsion. The ability of attraction repulsion means the strength. Here it exerts more repulsive force, means it has more pole strength. It exerts less repulsive force, it has less pole strength. Pole strength is represented by letter small m. Okay. Now we can treat this bar magnet. Pole strength is represented by m. Now one more point I am going to write. Here the bar magnet, if you see this bar magnet, whatever the properties possessed by north pole, this north pole have the same properties exhibited by positive charge. North pole have the same properties exhibited by positive charge. South pole has the properties exhibited by negative charge. South pole act as a negative, north pole act as a positive. So I can write this is positive, you can understand clearly. So north pole has the properties of positive charge, south pole has a negative charge. So here I can treat this bar magnet as a magnetic dipole. I will write what is meant by dipole. If equal and opposite charges separated by definite distance is known as electric dipole. In the same manner, magnetic dipole. Two equal poles, I will write the definition. Magnetic dipole. Magnetic dipole. Equal and opposite poles. Equal and opposite poles. Opposite poles separated by finite distance equal and opposite poles separated by finite distance is called magnetic dipole. See, assume this is a here it is, I am keeping a south pole whose pole strength is m, I am keeping a north pole whose pole strength is m. Strength wise both are same, but they are opposite poles. Sir, in the magnet, in case of a dipole, all the distance are measured from the center. From the center, south pole is a distance of L distance, north pole is a distance of L. So here, length of the dipole equal to 2L. Length of the dipole equal to 2L. The magnetic moment, in the same manner, electric dipole moment, magnetic dipole moment, the magnetic dipole moment or magnetic moment is given by the formula m equal to, sir, either of the pole strength. We can take strength wise both are same, either of the pole strength, so this is small m, either of the pole strength into separation distance between, this is 2L. The magnetic dipole moment is represented by capital letter M equal to small m into 2L. This is about magnetic dipole, bar magnet as a magnetic dipole. Now, magnetic field lines. What is meant by field? We are going to discuss first, then we can discuss magnetic field lines. Magnetic field lines. Sir, irrespective of magnetic field or electric field, I want to explain the field. What is meant by field? The region or space around a body. If you consider electric field, that is a charged body. If you consider a magnetic field, that is a magnet. The region or space around a magnet in which its influence is present. What is meant by influence? If you place any other charge, I will write in detail. Sir, this is a magnet. Sir, here it has two poles. Assume like this. So, in this region, if I place any magnetic needle, then this magnetic needle experience either attractive force or repulsive force. That region is known as field. So, this region is called field. So, since it is this field exhibited by magnet, this is known as magnetic field. This field is exhibited by whom? Magnet. So, this is named as magnetic field. So, if you see, this is charged body, this is plus Q. Around this, if I place any charged body, it experiences the repulsive force or attractive force. This field is created by charged particles. So, this is known as electric field. Either electric field or magnetic field, that is nothing but the region or space around a charged body or a magnet in which its influence is present. What is meant by influence? It either exhibit attractive force or repulsive force depending upon the pole which is present towards it. This is known as field. Now, the magnetic field is expressed easily in terms of magnetic field lines. Now, how we can draw a magnetic field lines? In the same manner, what is meant by electric field line? In case of electric field line, what we can say? The path followed by unit positive charge. In the region of electric field is known as electric field lines. In the same manner, the best way to represent the electric field lines by using magnet needle. Sir, assume this is a bar magnet. I am taking a magnetic needle in the form of arrow like this. Sir, this head is head I am taking as north pole, tail I am taking south pole. If I place this needle, magnetic needle here. So it experience south pole experience attractive force, north pole experience repulsive force. So like this. So here I will write like this. I will trace a point like this. Now this needle I will move from this position to 1 minute. I will write clearly. So this is the, I bring the magnet needle here. So magnet needle shows in this direction. First I keep. So here I will keep 1 point. This needle I will move in this direction. Here it will direct in this direction. Once again I will keep this needle. So the direction in which the magnet needle moves, that gives the magnetic lines of force. In the same way, if I keep here, it will move. So magnetic line of force starts from north pole, ends at south pole. So this is the like this. The path followed by magnetic needle in the region of magnetic field is known as magnetic lines of force. South pole, in case of south pole, field lines are inwards. In case of north pole, field lines are radially outwards. In case of north pole, field lines are radially outwards. Field lines are radially outwards. Outward field lines indicates north pole. Inward field lines indicate south pole. So in case of south pole, field lines are inwards like this. So this is inwards. If you draw one more line, this is inwards. Now properties. I am going to discuss properties. First property of magnetic field lines. This is the first property. They form closed loop. They form closed loop. Next property. The tangent drawn at a point to the magnetic field line, the tangent drawn at a point to the magnetic field line gives direction of magnetic field. So see, this is a point. I want to know the direction of magnetic field at a particular point. So at this point I want to know direction. Draw a tangent. The tangent at that point gives the direction of magnetic field. At this point I want to know direction of magnetic field. Draw a tangent. The tangent drawn at a particular point gives the direction of magnetic field at that particular point. Next, third point. The magnetic field strength is expressed in terms of magnetic field lines. Sir, assume the number of magnetic lines. Sir, what is meant by electric flux or magnetic flux? The number of magnetic lines of force passing through a unit area in a perpendicular direction. I will repeat one more time. Sir, assume this is a surface. This is a magnetic field lines. The number of lines of force passing through an area in a perpendicular direction. Sir, please look at here. Here this area and magnetic lines are mutually perpendicular. Here this area is making an angle. I can take component of area. See, assume this is area making an angle. I will take component of area in the direction of magnetic field. While when we are calculating the magnetic flux, we have to take the component of area in the direction of magnetic field or the area which is perpendicular to the magnetic field. Okay. See here, assume that is known as flux. In this case, assume this is unit area. In this unit area, the number of magnetic lines of force are passing 1. Here, this is 0.1 I can write. If you consider same area, here the number of magnetic lines of force passing through this point is, I will take this is 2 point. So I can say clearly, field at 2 is more. Why it is more? Here the number of magnetic lines of force passing through this area is 3. At this point, number of magnetic lines of force passing through this point is 1. So when compared to 1, at 2 magnetic strength is more. Based on the magnetic lines of force, we can say the strength of magnetic field as the number of lines passing through the area is more, then field is more. Number of magnetic lines of force passing through a unit area is less, then magnetic field is less. So it is expressed in terms of flux number, flux density, magnetic flux density. Next, they never intersect each other. Third point, they never intersect. Sir, why they never intersect each other? I already mentioned, assume this is the field line, this is the direction in which moving. Assume these two lines are intersect. Then where the direction, in which direction the magnetic needle moves? The magnetic needle follow unidirection. So if they are intersect, the magnetic needle has a 2 ways to move. This is contradiction to the regular phenomena. So we can say they never intercept each other. We have to remember these are the properties of the magnetic lines of force. This is the properties magnetic lines of force. Now we are going to discuss bar magnet as a solenoid. This is important derivation and easy also. So before going to discuss this bar magnet as a solenoid, I want to explain two results that already you know. Magnetic moment of a current carrying loop. This is a current carrying loop whose radius is A. Whose radius is A, having n turns. Magnetic moment of current carrying loop. This is magnetic moment. Magnetic moment of a current carrying loop. Current carrying loop M equal to NIA. Here N is the number of turns, N is the number of turns, A is the area of cross section, area of cross section, I is the current. I is the current flowing to the conductor. Next. Now, what is the magnetic field produced by current carrying loop? This is current carrying loop. So, if the loop is in the form of circle, then magnetic moment M equal to N. If it has number of turns capital N, I can take capital N or small n, that is nothing but total number of turns. N I pi A square. It is a loop. If it is a circular coil, I can take instead of pi r square, I can take L square. Magnetic moment is called Ni pi A square. If it is a circular loop, for circular loop. This is for circular loop. For circular loop. In the same manner, I want to write one more formula. Magnetic field due to a current carrying. So this is a circular loop, current carrying loop. This is center at a point P. This P is a point at a distance x from the center, whose radius is A. Then what is the magnetic field produced by, it has n turns. In this case, magnetic field produced by circular loop is given by the formula B equal to mu naught Ni A square by 2 into x square plus A square whole power 3 by 2. These two derivations already we studied in moving charges and magnetism. We can use these two derivations to explain bar magnet as a solenoid. See, this is the formulas, these two formulas we can use. Please remember this. B is equal to mu naught Ni by 2 pi mu naught Ni A square by 2 into x square plus r square. Sir, I am multiplying numerator and denominator with 2 pi. So, we will get mu naught by 4 pi into 2 pi into mu naught Ni A square by x square plus A square whole power 3 by 2. This formula we can use easily. Mu naught by 4 pi is a constant in magnetism. So, this is the most generally used formulas. To understand this upcoming derivation, these two things we have to understand. Magnetic moment of a current carrying loop is Ni A. Here A is the area of cross section. So, Ni pi r square. Magnetic field produced by circular current carrying loop is B equal to mu naught Ni A square by 2 into, here x is the distance from the center to the point P, A is the radius of the circular loop. These two formulas we are using now. Here, bar magnet as a solenoid. Comparison of bar magnet with solenoid. If you see, the concept name is bar magnet as a solenoid. So, if you observe, the magnetic field lines produced by bar magnet and solenoid is same. So, we can compare the bar magnet with the solenoid. So, I am taking a bar magnet. I am taking a bar magnet whose length is 2L. This is the center. Assume this is north pole, this is south pole. This is the center. This is the center. From the center, south pole is at distance L, north pole also at distance L. I want to find magnetic field at a point P. I want to find magnetic field at a point P. So all the distance are measured from the center already you know. So I can take the point P which is at a distance r from center. Next, I am going to assume an elemental portion, elemental ring, elemental length dx, dx which is at a distance x from the center. I am going to assume. Now I am going to write the some data. Here A is the area of cross section. A is the area of cross section of the bar magnet. I am going to consider this is cylindrical shaped bar magnet. Now I will write let A be the radius of the bar magnet, radius of bar magnet, small n be the number of turns per unit length, be the number of turns. Number of turns per the unit length. Sir, what is the total length of the bar magnet? 2L. So, total number of turns, how we can write? Total number of turns. Total number of turns is called n into 2L. That will be capital N. Total number of turns, capital N is equal to n into 2L. Sir, if n is the total number of turns, the number of turns present in the dx length, I am going to write that is dn. The number of length, the number of turns present, number of turns present over the length, number of turns present over the length, dx. Dx is I am going to write dn. dn is equal to n into dx. Okay. Now, sir, I want to find this. I am going to consider this elemental ring. This elemental ring, please look at the board. This elemental ring has dn turns. Sir, the because from center elemental ring is a distance x. From the point P, how much distance from the elemental ring? This total distance r. This is x. So the point P is a distance of r minus x. The point P is at a distance of r minus x from the center. So this from the elemental ring. The point P is at a distance of r minus x and the radius of the ring is A. Sir, the ring has dn turns, radius A, the distance of the elemental portion, from the center of the elemental portion, the point P is at a distance, r minus x. Now, here what is the magnetic field formula? In the last class we did, in the last section I explained B is equal to mu naught Ni A square by 2 into x square plus A square whole power 3 by 2. This is this formula already mentioned to you. So, in order to remember the formula for long time, I can write mu naught by, I am multiplying numerator and denominator with 2 pi. So, mu naught by 4 pi into 2 pi Ni A square by x square plus A square whole power 3 by 2. Now, here what is the value of x? Here value of x is r minus x and A is A. If I substitute dB, magnetic field at P, dB I will write what is meant by dB. dB is the dB equal to magnetic field at P due to elemental portion dx. I am repeating one more time. Sir, what are the things we are going to take? I want to compare the bar magnet as a solenoid. How we are going to compare? The magnetic field lines produced by the bar magnet and solenoid both are same. So, I can treat the ring bar magnet as a solenoid having an infinite number of circular coils. Here I can take a bar magnet in the form of cylindrical shape. This O is the center of the bar magnet. I am assuming a elemental portion at a distance x from the center whose thickness is dx. This is the assumption I am taking, and here let r is the radius of the bar magnet and n is the number of turns per unit length. If n is the number of turns per unit length, what is the length of the bar magnet? Length of the bar magnet is distance between two extremes 2L. So, I can write total number of the turns is n into 2L. Okay. Now, I want to find, sir, first I want to find magnetic field due to the entire rod, but it is not possible. So, what I am going to do, I will assume an elemental portion. Because of this elemental portion, I will find the magnetic field at P. After finding, I will integrate for whole the things. Sir, from if we consider this is O, one end is at a distance L, other end is at a distance L. So from the center, it is, we can consider this is negative x direction, this is positive x direction. So the elemental portion ranges from where to where? Minus L to plus L. I can find magnetic field due to the elemental portion. After finding magnetic field, I will integrate this expression between the limits minus L to plus L. Then I will get the magnetic field for the entire portion. This is the thing I am going to do now. Here I want to find magnetic field dB. What is dB? dB equal to mu naught by 4 pi. I will keep 2 pi x. 2 pi, how many turns are there? N turns. Here how many turns? Dn turns. Dn turns, radius A is same. I current is flowing, A square I R A square I by, I can write R minus x whole square plus A square whole power 3 by 2. Sir, if R is far greater than, if R far greater than x and R far greater than A, this is A, we can neglect x and A. If you neglect x and A, I can get, sir, 1 minute, I think it is not visible, 1 minute I will write, sorry. dB, I will write dB clearly, dB equal to mu naught by 4 pi, as it is mu naught by 4 pi 2 pi. This elemental link, how many times it has dn? How much current is flowing? I current, radius A square pi. What is the distance? R minus x whole square plus A square whole power 3 by 2. This is the magnetic field due to the elemental ring. Now what I am going to do? Sir, after finding this elemental portion, I want to find what is dn. dn, now only we derive dn is equal to n into dx. So I will substitute that also, mu naught by 4 pi into 2 pi n dx I A square by R minus x whole square plus A square whole power 3 by 2. I already mentioned, if x far greater than x and R far greater than A, we neglect x and A. If you neglect x and A, then what you will get in the denominator? The total term R minus x whole square plus A square whole power 3 by 2, we can write directly R cube. If you write, then what we can get? dB equal to mu naught by 4 pi, mu naught by 4 pi 2 pi n A square I A square by R cube into dx. I bought all the constants outside. Then finally what we will get, sir? This is the thing we are getting. Now I want to get the total magnetic field, not for elemental portion. So if we integrate this expression between the limits minus L to plus L, we can get the total magnetic field. To get the total magnetic field, at P, integrate above expression between the limits minus L to plus L. If we integrate this expression between the limits minus L to plus L, we will get the total magnetic field. Now, sir, I am rubbing this portion only, small portion, and I am also rubbing this. Now I am going to integrate this expression. So I can write B equal to integral dB from minus L to plus L. If you write all the terms outside, mu naught by 4 pi into 2 pi n a square I by r cube as it is integral dx minus L to plus L. Sir, dx and integration x mu naught by 4 pi into 2 pi into n a square I by r cube, this dx and integration x, so minus L to plus L. After integration what we will get, sir? First we have to substitute upper limit minus L, sir, L minus of minus L, 2L. So this total value will get 2L. That is upper limit mu naught by 4 pi 2 pi into 2 pi by r cube into n I a square by n I a square into 2L. Sir, I will rearrange the terms. Mu naught by 4 pi I will keep as it is, 2 also as it is, n into 2L I will write one term, into I will write one term, pi a square I will write one term. Then sir, here n into L become total answer only, no? Capital N is equal to small n into 2L, pi a square, capital A is equal to pi a square. Then finally what you will get, sir? You will get mu naught by 4 pi into this NIA. So m equal to what the formula? NIA only, no? Sorry, this is A is the capital A. Capital A is the area of cross section. So this term all together become NIA. So I can write 2m by r cube. So we are getting magnetic field produced by bar magnet same as magnetic field produced by solenoid. So this is the comparison of bar magnet with solenoid. So thank you. Up to here prepare well. Tomorrow we will continue the next class.